Yeah. So, good afternoon once again. My name is Nikhil and I'm doing my master's in sustainable energy in the University of Cork. So, as per my dissertation, I have done a techno-economic model for airborne wind energy system. So, I am trying to present my findings today in this presentation. So, this will be how we are going to do today. First, I will have an introduction about what the airborne wind energy system is, a small introduction. Then I will talk about what was done in the techno-economic model. And I have done a case study in Bangalore Airways and what are the results at the end of the day. So why we are going for the airborne wind energy system is because there's a huge demand for the clean energy systems nowadays. And we have seen that the wind energy has grown exponentially over the past 2 decades. And wind energy takes up a lot of space for the setup, and it is really hard to set up. So I am trying to, and it is having a capacity factor of between 30 and 40. So that's much lower. And this new technology, airborne wind energy, is expected to have much more better energy capacity. So what is airborne wind energy system is that it's a system that is used to take the wind energy from the high altitude of 300 to 600 meters, because the wind there is much more stable and much more stronger than what we experience in the ground, 100, 150 meters. And this technology uses a tether and an aerodynamic device to absorb the kinetic energy of the wind. So the materials that will be used for the system is much more lower than what we actually see in a normal wind turbine. So there are 2 different ways in which this wind energy is harnessed using this technology. One way is we fit small generators on a kite or a flying device, and we fly it over to 300 to 600 meters, and we use that to produce the energy on board the kite, and then that is being transferred back down into the ground station. Or the second method is that the generator is kept in the ground, and we use the kite to create a H-shaped movement, so that the wind just is pushed and pulled, rolled out and rolled in, and this rolling motion will create the energy in the generator. So in here, I have taken the economical study for 3 different models of the airborne wind energy system. One is called pump mode with kite, where we are using a kite for this for the harnessing of the energy. Then there is a pump mode with glider, where we are using a glider instead of kite for harnessing. And then the flying wind turbine, where the wind turbine is attached to the kite and to generate energy in the sky. So these are the 3 models. The first model, as I told you, we are using the kite, and because of that, the initial cost will be much lower because there are no rigid structure for that. But since it is using kite and really thin materials, there is a chance of operational cost is going to be much more higher than the normal ones. So, and there will be more maintenance break will be much more frequent. The second one, instead of kite, we are using a rigid wing that will allow for a much more higher lift by drag ratio, which will be able to make much more higher wind conversion to the kinetic energy. But the problem here it is that we are using a much more harder substance, so it will cause much more in the initial stage, or the capex will be much more for this one. And since it is a rigid structure, we will be needing a much more larger area for the launching it into the sky. And the third one is the flying turbine, in which this one is like what is happening, and the turbine is attached on a helium balloon that is floated over in the sky in a particular height. So this is, in terms of like maintenance, it has less maintenance. The only thing that it requires is the helium that is needed to be replenished every once in a while, and the helium is much more costlier. And because of all these three structures, this one is the most heaviest one. So for the techno-economical model, what I did is that I took the site Bangor Airways, and I took the wind resources from the area. Then I put into the power wind resources. Then the three models of the models are taken, and then their power curves are taken into account, and they are put in the formulas, and the power energy yield is found. Then the LCOE and the return are being calculated. Then since this is a maturing technology, most of the data available are like the companies that are doing the tests are keeping the data to themselves, and very few data is really available to us. So some part of them are being assumed. So a sensitive analysis is taken into consideration to tackle that problem. So for the techno-economic analysis, I have taken the project lifetime to be 15 years, since it is much more less material, so it wears down more faster. And the discount rate is taken as 7%, and it is one thing is to be clear that this is for 2030, not for now. So the electricity price is taken as 10 cents per euro per kilowatt hour, and the energy degradation rate is taken in between 0.5 to 1% per year based on the model. And the labor cost is taken into account, the connection, battery storage. These are taken into the account for the system. And these are the formulas that have been used to figure out the economic values of the system. The levelized cost of energy, it is the minimum price per unit of electricity for which the project will even for the lifetime. That means that if the electricity costs this much, then that is the minimum. The electricity should cost this much amount of price, so that the system will be very good. Like if it is like, if the LCOE is like 10 cents per kilowatt hour, then at least the electricity should be sold in 10 cents per kilowatt hour for the project to be viable, economically viable. For the net present value, it is the difference between the current revenue and the value of cost over the project lifetime. That is to understand how the value of the project will change over 5 years, 10 years, etc. And the internal return, rate of return, is the value at which the discount rate at which that has to be taken, so that when the discount rate at which NPV will be zero, so that is represented by IRR. And normally a project is taken as viable when IRR is between about 8 to 10%. And for the case study, as I said before, like Bangor Airways has been taken. This was based on the study done, and the findings was that it has one of the strongest wind in the higher altitude area, and it is much more less populated area. It's like a rural area, and since this system is working kind of like 300 to 400 altitude section, there's a restriction in the aviation department also. Like there should not be any accidents while you're flying this with any other kind of like airplanes or any kind of drones shouldn't crash with us. That should be also taken into account. So this AI is kind of like the best right now in Ireland. And actually, many of the startup companies that are doing projects in the system have their testing sites situated in this Bangalore areas. So when the wind data was taken at 500 meters, because that was the most reliable data that was available for me to be taken, it was taken from ERAS 5, and the data was verified with Arishmet. And I found out that the mean wind speed was about like 11.72 meters per second, that area, with a wind power density of 1,550 parts per meter square, and the temperature is about the range of -2 to 20 degrees there. Then the wind data was fitted into the Weber's distribution, and it was the C and K was found out. And this K and C was used to find the annual energy production of the area. And based on the papers that were given out by the companies, the pump kites are normally taken in 30 kilowatts. The pump gliders are like normally working in a single unit will be like about 50 kilowatts, and the flying wind turbines are normally in the range of 100 kilowatts. And I was able to figure out that the annual energy production in the Bangalore was like 155,000 kilowatt hour for the pump kites. And for pump gliders, it was like 235,000. And the flying wind turbines were about 443,000. And it clearly states that this capacity factor for each of these technologies were in the range of 50s in this area. And it is clearly much more in terms of technical wind energy production base. This technology is having a much more advantage than the normal wind turbines. But when it comes for the financial state, that's where the problem starts, because this technology is relatively new. There is less research going on. So each of this system was having a high capital investment and high operational cost. The operational cost is more because they use much more lighter material, which makes more maintenance interval and more maintenance need to be done to them. So each of them cost like this much values around the year. Like for the kites, it was like 95,000 euros around for the initial investment. For the gliders, it was like 178,000, and for the flight gen, it was like 628,000. And an operational point of view, it is like 10,000 per year for the kite, and for the gliders, it is like 15,000, and for the flight gen, it is like 33,000 for a single unit of them. And the LCOE, and NPV, and IRR was calculated based on this, and it was found that for each of them, it is in the range of 0.14 to 0.24, which is much higher than what we have for the wind turbines, which is around 0.1. And the IRR also is on the negative. So in order for the project to be viable, we have to have the IRR at least in the 8% or something. So on that basis, these projects are financially not a viable one right now. But these are that is because this is like in the mature state, and there are a lot of resources that has to be done, and better materials can be introduced in order to reduce the cost in many of the regions that are right now costly. So then I have done the sensitive analysis based on this. The parameters that I have done the sensitive analysis was for mean speed. I just consider the speed to be varying 10% more or 10% less. Then I consider the system to be 5 more years lifetime, or like a normal wind turbine. Then there was another calculation based on what will happen if the capital cost is being reduced, or what if the electricity cost is being increased. And it was found that whenever the wind speed is more, the LOC will be reduced by 15%. Same goes for the system life also. If the system life is more, then also the LCOE will be reduced. Same like IRR also will be increased by 6%, which will be massive. And if the electricity is being taken like 0.12 euros per kilowatt hour or 0.14 euros per kilowatt hour, then that will increase like 10% in the IRR. So this is like the analysis comparing each of them for the sensitive analysis, and it was saying that like the areas we can improve is like we can use a material that is high module polyethylene tethers can be used to connect the ground generators to the flying kites, which are light and which will be much more cost effective. So these tethers are being right now in the research stage. So we hope that it comes out as positive and it can actually reduce the cost of the wind turbine. Sorry, for the first system. And there's another challenge is for the flying generation. For them, it is the helium, which is of high cost and of low availability. And the opportunity here will be like for a production of these local materials for the tethers or other spare parts here in Ireland can be of good use for the economy of the country. Then when we are considering localization to the Ireland is having an 18% renewable target by 2030. So this can be actually a useful technology that can be used for the future. And also that the airborne wind energy system, as it is like, it's railing out, railing in. So the power output will be a little bit sinusoidal. So there will be a smoothing system should be also be considered for it. And another challenge is that we can increase the altitude at which the wind is collected. This has to be done with the help of like the IAA, which is the Airspace Authority of the Ireland. Then another way we can support this system is by the renewable RSS subsidies that can be used for this system, which can help in reducing the LCOE to up to 10 cents per kilowatt hour, which will be a valuable one. One of the major advantages is that the land use will be much lower for this system. But there will be other challenges like the birds can hit them because it is much more higher than cause much more danger for the birds and all. So that studies has to be done more in terms of that. And as a conclusion, I will say this system is something that in a technical point of view, it is a wonderful replacement for the normal wind turbines that is now available, but it has a long way to go. It's still in the mature state, and financially speaking, it is still not very good or good one. But it can be also used as a complementary with right now with the wind turbines and all. We can start like that. Maybe in the future, like how wind turbines were able to be integrated into our system, this system also can be brought into light and be a useful one in helping us transiting from the fossil fuel system to the clean energy systems. Thank you.